All right. Good day, everyone, depending on where you are joining us from. Today is another day for PSI webinar series, and I'll go through the webinar agenda for today's presentation. For the agenda today, we'll have an opening remarks to be given by a member of Academic Planning Committee, PSI, Dr. Basira Kankia, and then this will be followed by introduction of our guest speaker, which I'm very sure most of us know him, but formally, we are going to give you a brief introduction about who he is. And then we'll have the main presentation of the day, which is to be given by Dr. Mustapha Mohammed from from Qatar University, Doha, Qatar, who will be taking us through a presentation about how we can apply or a guide to application of different biostatistical methods in our health research. And then you have question and answer session, and then we'll have closing remarks from the same Dr. Basira Kankia, and then presentation of certificate to the guest speaker. So like I said, before we commence, we always have this announcement. Number one, this webinar is being recorded, and as usual, the link to the webinar recordings will be shared with all participants via an email that will be collected much later during the webinar. And a link will be shared on the chat box where you'll be asked to provide your name, your email address, where we are going to send the webinar recording, your certificate of participation, and the webinar slides. And you can also contact us by just replying to those emails we send to you containing your certificate. And during the webinar, you are free to ask your question, make suggestion and observation through the chat box of the Zoom chat box. The first item in the agenda is the opening remarks by Dr. Basira Kankia. Dr. Basira.
Good morning, everyone. You're all welcome this Saturday morning, evening, afternoon, wherever you are. So a brief overview of Pharmacy Scholars Initiative. The Pharmacy Scholars Initiative is a mentorship network for pharmacists with a keen interest in research and career development. It was founded in December 2017. And it's registered with the CAC here in Nigeria. So we have membership from different parts of the world. So today's webinar is titled Practical Application of Statistical Methods in Health Research, and it's going to be presented by our esteemed guest speaker, Mustapha Mohammed, who is also a member of PSI. He's an adjunct faculty at Qatar University Health at Doha, Qatar. So this webinar, it's a pleasure to have everyone here, and it's a very important topic, which is foundational to advancing our understanding and improving outcomes in health sciences. As we all know, statistics is not just about numbers, but it helps us in making informed decisions, particularly in healthcare and in making public health policies. So as we go through the webinar today, we hope to acquire practical skills that will help us in applying statistical methods effectively in our research activities. So whether you are a seasoned researcher here, or you're just starting, or you need some further improvement and guide, we hope we all have valuable takeaways from this webinar that we'll use in guiding us through our work. So everyone is welcome, and over to you, Dr. Jato.
All right, thank you so much, Dr. Basira. Yes, this is a brief about what today's webinar is all about, and I'm sure you get to know details about what it entails as we move into the next item. So who is our guest speaker? So our today's guest speaker or facilitator is Dr. Mustapha Mohammed. And Dr. Mustapha Mohammed is a clinical pharmacist and educator with extensive experience in teaching, research, and clinical practice. He holds PhD in clinical pharmacy from University of Science Malaysia, master's from Near East University Cyprus, a PharmD from University of Benin, and BPharm from Ahmadu Bello University, Zaria, the Procedure University. Over his academic career, which spans more than a decade, he has held various positions, including lecturer at Ahmadu Bello University, research officer at University of Science Malaysia, and a faculty member at the health sector of Qatar University. Dr. Mohammed had vast research and editorial experience, currently serving as an academic editor for PLOS ONE and Frontiers in Antibiotics Bacteriology, and as a senior collaborator with the Global Burden of Disease Network. He has contributed to numerous impactful publications and conferences across a wide range of topics in basic clinical and population health. His current research focuses on the application of digital technology in public health, mental health, youth well-being, and health professionals. Join me in welcoming Dr. Mustapha to the podium for his presentation. Mr. Mustapha. Oh, sorry, there's more to hear. Dr. Mustapha is an active member of several professional bodies, including the International Pharmaceutical Federation, FIP, the International Society for Pharmacoeconomics and Outcome Research, ISPOR, the Pharmaceutical Society of Nigeria, the Nigerian Association of Pharmacists in Academia, and the Pharmacy Scholars Initiative. In the Pharmacy Scholars Initiative, he's not just a member, he has been a mentor and also an active member of Academic Planning Committee. In his leisure time, Dr. Mustapha enjoys watching, playing, and gaming football, and this is to extend his physical and mental fitness. He's currently dedicated to collaborating on multidisciplinary health-related research and the community services that align with his interests and institutional goals. So if you are looking for any research collaboration, you may likely need to contact Dr. Mustapha. Dr. Mustapha, the floor is yours.
All right. Thank you so much, Dr. Abubakar Ibrahim Jato, for that wonderful introduction. First and foremost, I would like to welcome each and every one of you to this very important discussion. I would like to share my screen and just to be sure that it's visible for all. I'm not sure that my slides are visible. Can somebody just give me a heads up?
Yes, visible. Yeah, it's visible.
Yes. Perfect. So today, inshallah, we're going to be discussing about practical application of statistical methods in health research. I'm very sure a lot of us are very much excited to listen to what we're going to discuss today. Statistics is one of the most important ingredients of research, and especially we are from the health sciences. Statistics is very important, especially because we are trying to discover or prove particular intervention that we believe should be beneficial to humans. And of course, we don't want to just be simply giving out things that has to do with guess. So we want to provide inference to something that we are very, very sure that whenever it's being utilized, the benefit will surely outweigh the risk. So the presentation is going to take two parts. Initially, I will start by demonstrating to us some few basic theories regarding statistics. And then towards the end, we're going to have some practical demonstration on how we can apply some of this statistical tests. Now, this is just a dossier that I want to begin with. There's this paper that we as the Pharmacy Scholars Initiative collaborated in publishing. And this work is come as a result of some casual conversation among us, where we historically noticed some trends in some of the publications coming from back home in Nigeria, where people use any kind of statistics in analyzing their data, regardless of whether that statistical test is valid or not. So initially, I think right from time when we joined academia, we noticed that people used to use t-test. Any paper you open that has to do with statistics, you will see student t-test. So later, the trend changes. So people are no longer using t-test. They were using ANOVA. And to them, it's an advancement. So even the t-test, there were issues. The ANOVA also, there are quite a lot of issues, because when you look at those studies, you find out that the application of ANOVA shouldn't be actually be there. So we thought that we can be able to bring out some information. Probably people that don't know would have an idea that these are the issues that we have because of that lack of knowledge, wrongly applying statistics. And then we did some kind of survey among visible database. We cannot, because some of those research are actually from local journals. So we thought if we can be able to identify a database that captures researches that are conducted from developing world like Africa, then we can be able to make some inference to what are the proportions of those statistics that are actually being conducted wrongly. So we are very precise in our research. We just picked ANOVA specifically. And then we are able to identify over 21% of the screened articles must have used ANOVA wrongly. So I believe this is a very critical issue, which if you take 10 articles, meaning out of those 10 articles, you are likely to identify up to 3 that have wrongly used ANOVA in this particular context. So like I said, we are dealing with health, and then we don't want to be bringing out things that are just based on chance. We want to be certain and be sure of the conclusion or inference that we are giving for the general population. So also, this is what actually prompted this discussion today, because we want to see how we can be able to improve our understanding of statistics, so that we should avoid being part of this 21% that are adopting statistics only. So this is just an overview, just to lay the foundation. Statistics is all about gathering and analyzing data. And then, of course, in statistics, we have some key elements, which are the ingredients that we need when we are discussing statistics. Data is something that we always use. Data is actually the crude oil of research. So this data can take different forms, especially when it comes to statistics. So generally, we can say that data can be divided into two. Either the data is continuous or is numerical. But of course, for the purpose of today's presentation, and especially because we're going to use a particular statistical software to demonstrate how this data can be actually play around. So we choose to divide the measurement level into 3. We have what we call nominal, we have what we call ordinal, and we have what we call scale variables. So nominal variables are variables that are mostly categorical, they are discrete. For example, when we are talking about gender, where you have male and female, where there is no a particular order for that kind of level. Or for some of us that are into experimental research, those from pharmacology, when you have a treatment group where you have control, you have a treatment, the control can be either positive or negative control. So all those groupings are what we termed nominal levels of measurement. Then when we have a nominal data, but then that nominal categorical value is being ordered, there is a ranking in the arrangement. So that categorical value, we can say that is an ordinal data. Practical example is when we are having like cancer grades, can be stage 1, stage 2, stage 3, where one level is either less or more than the other. Likert scale for some of us that conduct social research, where you ask your target participants to like rate the level of satisfaction or their perception about something, where you have some sort of level from maybe either agree, strongly agree, neutral, don't agree, or strongly do not agree, something like that. So those are ordinal. Then we have what we call the numerical variable. Generally, in this platform, we may be using a skill. We have two major components of skill, like the interval levels and then the ratio. Intervals are things that has to do with no zero values that zero doesn't actually have meaning. For example, temperature, when you have like some kind of continuous values like 10 degrees, 20 degrees, 30 degrees, where you cannot say that 20 degrees is like 2 times heater than 10 degrees in that direction. Then we have ratios which are like age, weight, height, all these that have actually true zero. We can refer to them as skill variables. Then generally in statistics, and then later we're going to be using these categorizations. Variables are divided into two. It's either the variable is dependent variable or the variable is independent variable. Dependent variable is our factor. Sometimes you can see them using what do you call them? Predictors or the input, and then or risk factors sometimes. It depends on actually the context. Then the dependent variables are the outcomes we are looking at, the product of the research, as in what you actually measuring at the end of the research. So in statistics also, we have majorly two different statistical types. It's either the statistics is basic, which is just to summarize the data. We call it descriptive statistics. Then if you want to make inference, you want to judge, you want to make some claim or assumptions. So you go with inferential statistics. So in inferential statistics, which is very important, that's when you make those claims and then justify whether those claims are right or wrong in your study. So this is just some few examples of descriptive statistics where you summarize your data into some kind of snapshot where you want to see the distribution. For example, if you check the frequency or percentage, or you want to check some of the measures of central tendency like the mean, you want to find out the mean of a particular population, and then of course the dispersion, which has to do with the standard deviation. So all these are applicable when it comes to analyzing your study. When you conduct a research, the initial thing that you want to have an idea about how the data generally look like. So this can inform or guide you in proceeding to the inferential statistics. So this is very important. So here I just try to give us an example of one of our pioneer paper. This paper is one of the initial paper we published as Pharmacy Scholars Initiative. It was led by Zayanu Shitu. And then this paper, we're trying to identify the factors that can predict interest in practice-based research among pharmacists. So I'm just trying to demonstrate descriptive statistics, how it is presented in this paper. We normally, generally in most papers, if you check biomedical papers, the first table is the one that actually summarizes the study. It gives a like snapshot of the study. So like this one, we can see that we just summarize the socio-demographic characteristics of the study population who are pharmacists. So you can see where we have the frequency and percentage, how many females we have, 69, and in percentage we have 34. Males also we have 134 and 66%. So this is just to describe what is the distribution of gender among this pharmacist population. So also like age, because age is a continuous variable, we actually try to describe it based on mean and standard deviation. The mean value of the participants was 28.5 and then 2.2 as the standard deviation. So anytime you are conducting research, it's very important to understand and have like a clear snapshot of your data, or so that you can be able to have a guide in your subsequent analysis. This is also another paper. This is one of our star paper. It has quite a lot of publication indexed in a lot of databases and even cited by WHO. This paper was led by Dr. Shaban. So in addition to mean, median, percentages, descriptive statistics can also summarize your data in charts. If you summarize your data in charts, you can be able to also have a clear snapshot of how the overall data look like. This is just a map based on the distribution of COVID-19 information overload. We had a global study where we take data from different regions and countries around the world, and then we summarize it in form of a map. Then this one is just after collecting the data, because the data is continuous, we generated a score. This score is called COVID-19 overload score. And then because it's continuous, we just want to have an idea how that data is distributed. So this is just a histogram to show the distribution of the data. Now, the second aspect of statistics, which is very important, is the inferential statistics. And in inferential statistics, like I said, we want to make inference. We want to actually check for any relationship. Relationship can be either difference, it can be either association. So there are basically two forms of inferential statistics. We have what we call the non-parametric test, and we have the parametric test. So when we talk about non-parametric test, we are talking about a data that is actually not normal in a sense. So not normal meaning it's not actually distributed normally. You cannot say that the data is distributed normally. Normally, if you collect the data from a population, you expect more than 95% of that study population to have some kind of similar characteristics in a way. So if you plot, for example, a histogram like the one I showed previously with our COVID study, you can be able to see the distribution, how that data is being distributed. So if the data is skewed, meaning you have more of higher values than the normal values, we call it right skewed. If you have more of the lower values than the normal values, we say the data is negatively skewed. And this is important when determining which particular test you need to do. Automatically, when the data is categorical, especially the dependent variable, there is no point of even asking whether you should conduct non-parametric or parametric. Automatically, it will be non-parametric. So also, if you have your data, which is a continuous data, and it's normally distributed, this is what is called dumbbell shape. So if the data is normally distributed, there are actually tests, later I will show you. If the data is normally distributed and is continuous, so the kind of test that you should conduct for that kind of data is called parametric test. So also in statistics, inferential statistics, we mostly deal with hypothesis testing. You have a claim and you want to confirm whether that claim is right or wrong. So basically, in the hypothesis testing, we have two different types of hypotheses. We have what we call the null hypothesis, and we have the alternate hypothesis. Null hypothesis is just saying that there is actually no difference between whatever statistics you are looking. There is either no difference in means, no difference in median, no difference in proportion. It's a null. There is no actually difference. So that's what even prompts us to conduct the test to prove whether that claim that there is no difference actually stands or otherwise. So if, for example, you conduct the test and then you found out that there is actually a difference, then you have to reject the null hypothesis, because the null hypothesis is actually contrary to what you are actually getting as the final result. So that's what brought us to alpha, which is level of significance, and p-value. Alpha is actually what you set as a researcher. You set a threshold saying that, okay, for you to accept or reject or not reject your null hypothesis, this is the particular acceptance rate. Okay, this is a particular level of chance that you can allow. And that level of chance is normally set as less than 0.05. So you are certain that whatever the outcome you get from your test, only 5% or less is happening by chance. So that's more of the component is actually the exact inference. So also the p-value, p-value is what you actually calculate from the test. So normally when you do the calculation of p-value, then you compare it to your alpha level. The alpha level, you can set it as 0.5 conventionally, but it can go as low as 0.01, 0.001, depending on how much precision you want in your study. So comparing p-value and alpha value, that's when you do your decision whether to actually reject your null hypothesis or not. So once the p-value is less than your alpha, for example, if we are using 0.5, then of course we reject the null hypothesis, because there is quite enough evidence to prove that there is actually difference in whatever statistics we are looking. Then in the event that the p-value is greater than alpha, for example, if the p-value is greater than 0.5, then we said we don't have sufficient evidence to actually reject the null hypothesis. Hardly you see people saying you accept. So you just say you don't have enough evidence to reject the null hypothesis. So this is just a practical example of comparing the p-value and alpha level that we can be able to make decision. So for example, they said the p-value for hypothesis is p greater than equals to 0.0256. What is your decision if the level of significance A 0.05, B 0.01? Like I told you, this level of significance is what you actually set. You can set it, but conventionally it's 0.05. So looking at this example, you can see that we have 0.02. 0.02 is actually less than 0.05. So if the p-value is less than the alpha, from what I said from the previous slide, we actually reject the null hypothesis, meaning whatever statistics we are looking at, there is actually a difference. There is actually an association. Then, in the contrary, when you set your level of significance as 0.01, if you compare it with the p-value here, you will notice that it's actually your p-value is greater than your alpha. So if the p-value is greater than alpha, then you cannot reject the null hypothesis. You just say you don't have sufficient evidence to reject the null hypothesis. And then the result is statistically not significant. So how do we choose statistical tests? There are basically a few steps which can guide you in choosing the right or appropriate statistical test. Like in every research, you should have your research question. What are your research questions? What do you actually want to do in your study? So research questions are mostly linked to your hypothesis. And then, for example, you want to check either there is difference in a particular parameter from a population. I will show you examples. When you see the examples, probably you would understand this better. So the hypothesis, you set the hypothesis, whether there is a difference, significant difference between the target uh, variable or not. Then you check the level of measurement. The level of measurement is what we saw initially, whether you are dealing with continuous data like age, or you are dealing with categorical data like gender. Then you check the parameter assumption. This parameter assumption is what we talked about also earlier, trying to identify whether we should use parametric test or non-parametric test. So in checking the parametric assumption, there are basically a lot of things you can do. There is what we call the normality test. You can check whether the data is normally distributed or not. And this can be done simply with some of the softwares that are available. You just run your data and check some of the, you can check through histogram, you can check through box plots, you can also check using normality test. We have two normality tests I will show you later that you can be able to make inference. There's Kolmogorov spin-off, there's Shapiro-Wilk. Shapiro-Wilk, if you have a smaller like data, or if you have a larger population or sample, then you can use Kolmogorov spin-off. Then the sample, how is the sample? Is the sample big enough? This is the sample size. Mostly, if you have a big sample size, the chances that the data is normally distributed is very high, and then you go for parametric test. And then if the sample is very small, the chances that the data is not normally distributed is also high. So normally, conventionally, sometimes you can use a cutoff of 10 or 50 or 30. There is no any like strict rule for that. But then the most important thing, try as much as possible to check whether your data is big enough or too small to make decision on the choice of test. Then the variance, this another parameter that you can check whether there is variation between the groups you are comparing. They call it homogeneity of variance, whether the variation is equal or not equal. So you want as much as possible the variances to be equal or homogeneous for you to go with parametric test. Then another steps that you need to check is how many groups are you dealing with? Especially this has to do with your independent variable. If you are dealing with only one group, then there's a particular test you do. If you are dealing with two groups, there's a particular test you do. If you are dealing with more than two groups also, there's a different test you can do. All this I will also give you example so that we can practically appreciate how this is done. Then also study design. Study design also is very important in choosing the right statistical test. Some studies are independent. Like you are taking the data that you are reporting is actually independent for each particular group. Then if you have the data that is dependent, meaning, for example, if you are taking a before and after from the same subject, this we call dependent, or this we call paired. Then if you are taking from different subjects, then it's called unpaired. You can look at it as before and after. You can also look at it as pre and post kind of, or repeated, when you are repeatedly taking a reading from the same subject in that fashion. So now finally you select the right statistical test and then decide whether you want to accept or reject the null hypothesis. So now, too much of explanations, we'll soon get to how we can practically do some of these things. Here is just the same thing that I mentioned previously. trying to choose between parametric test or non-parametric test. And then for parametric tests, you want to ensure that your population is normally distributed using all those normality tests. You want to also ensure that the variable is continuous, and then the observations are large enough for you to conduct parametric tests. So this is also very important. The whole conversations that we've been doing today is surrounding, as in it has to do with this table. How do you actually decide which test to conduct? Here we have two different types of tests. We have the parametric test, which are in blue. We have one sample t-test, we have student t-test, peer t-test, one-way ANOVA, repeated major ANOVA. All these are parametric tests. And then the ones in red are the non-parametric tests. We have the sign test, Whitney test, Wilcoxon test, what do you call it, Kruskal-Wallis and Fritzman. So you can see that we have two different types of tests. So what makes you decide which test to adopt is all these variables, whether it is one sample. If it is one sample, then you go for one sample t-test. If it is normally distributed, or if it is not normally distributed or fail any of the assumption of parametric test, then you go for sign test. Then if you have two samples can take two fashion like we saw. It's either is unpaired, which is independent, or paired, which is dependent. So if it is independent, you have two independent groups, and then it is normally distributed, then we go for student t-test. Sometimes you call it independent student t-test or just student t-test. So if there is any issue with the parametric assumption, whether the data fails the normality test or is categorical or not, then we go for what we call the Whitney test. I will demonstrate practically how all these things are. They are very easy to conduct. Then if the data is dependent, they are paired, meaning you have taken repeated measures from the same subject. Then if you have two measurements, two levels of measurements, then we call this test paired t-test. The parametric test here is called paired t-test. Then if by any chance it fails to pass any of these parametric assumptions, then we go for non-parametric test, which is called the, what do you call it? Wilcoxon sign rank test. Then if we have more than two groups, that's from 3, 4, 5, and above, then if we have the data to be unpaired, meaning the three groups are independent, all of them are independent, then the parametric test is called one-way ANOVA. Then if by any chance it fails any of those parametric assumptions, then we say we are to conduct Kruskal-Wallis test. So also if it is paired, 3 levels. If you have the 3 levels and then or more, and then the data passes the normality assumptions, then you conduct repeated major ANOVA. If it doesn't, then you conduct Fritzman test. So all this we are talking about continuous value. Continuous value, we just check normality and just whether the data is normally distributed or not. So this is a paper that was actually a collaborative paper from our PSI, which is being led by Dr. Mubarak. Dr. Mubarak did a very good job here, where we looked at the subacute toxicity of a particular extract of a particular plant. So for some of us that are into experiments, you will agree with me, experiments will have different levels, will have different groupings, like your control and treatment. So here we have distilled water as our control, and then we have treatments in 3 different increasing doses. So here, this table actually shows whether there is any significant difference in, you can take any of the parameter, like you can take ALT, AST, ALP, these are all liver enzyme blood liver enzyme parameters. So, and they are continuous because they are numerical. So if we want to check if there is any significant difference between the mean of these 1, 2, 3, 4 groups, so it's greater than 2 groups, definitely we are going for ANOVA. So that's why he conducted, or we conducted ANOVA. And then later I will explain to you about post-hoc test, because ANOVA will just tell you there is actually at least one variation or one difference among these 4 groups. But where the difference lies until when you conduct post-hoc, that is when you actually determine which pairs are actually different from the other. So there are different post-hoc tests. We can have DUNET when you are comparing only 2. If here we are just comparing with distilled water, that's why we use DUNET. So if we are comparing family-wise, like irrespective whether distilled water versus 250 versus 500, then there are other tests that we can do, other post-hoc tests. We have Banfaroni, we have Shife, we have Turkey, quite a number of them that you can actually adapt. So this is also another second study by the same Dr. Mubarak. And this is just to show you that you can actually present your results as table or as figures, just to demonstrate the test that you've conducted. Here we conducted ANOVA because the data is continuous, and then we have different groups. And then because here we did family-wise comparison, then instead of DUNET, we use Turkey. So we talk about continuous variable. What about if we want to check the differences using categorical variables? Categorical variables can also be 1 sample, 2 sample, or more than 2 samples. If it is 1 sample, it is the parametric test is just 1 sample difference of proportion. If it is because it's categorical, yeah, so only this an exception. Once it is categorical, automatically everything will be non-parametric. So also we have, when you have 2 sample, you want, if the sample is related, if it is related, then we conduct what is called McNemer test. If it is unrelated or independent, we conduct chi-square test. So chi-square test, in the event that you have any small, because in chi-square test, you are looking at the proportion distribution. So if the proportion distribution among the groups is less than 5, maybe one of the groups has less than 5 readings, then you have to go with Fisher's exact test. They actually do the same thing, nothing different. It's just based because of the smaller samples reading. That's when you go for the Fisher's exact test. So another one, when the samples are greater than 2, 3, 4, 5, is also the same chi-square, but in different formats. So there is also this example I want to show you, that we conducted a study. This is a study I led. We tried to find the factors that are associated with COVID-19 acceptance among university health science students. So this table, we are trying to compare the proportion of the different independent variables as against whether they accept or they don't accept the vaccination. So when you are comparing proportions, like I said earlier, we need to conduct chi-square. So if, for example, instead of 71 here, we have something like 4, 3, then instead of chi-square, we go for Fisher's exact test. Now, the second part after test of difference is test of association. If you want to check whether a particular dependent variable is associated with the independent variable, you can do basically 2 different association tests. The first one is correlation as a test, and then the second one is regression test. Correlation, you want to ensure that your variables are all continuous, both the IV and DV, and then the correlation, you're just trying to check the distribution, whether increase in IV leads to increase or decrease in DV. So you just want to identify the direction or the strength, whether they are correlated or not. And then you can have values between -1 through 0 to +1. -1 negatively correlated. Increase in one lead to decrease in one. +1 positively correlated. Increase in one lead to increase in the other. 0, no correlation. So when we have that kind of continuous data, you also want to check for parametric assumptions. And then if the data is normally distributed, you go with Pearson correlation test. If it is none, then we go for Spearman's correlation test, which is non-parametric. So regression, we also have different types of regression. I just pick two. There are quite a lot of them. So basically, the most common ones are these ones I listed, the linear and then the logistic. So in linear regression, you want to ensure that your dependent variable is continuous. You can have it as a stress level, pain score, blood glucose level, and then you want to predict using some different IVs. The IVs, independent variables, can take any form, whether continuous or categorical. So if you want to check how your IVs behave, then you go with linear regression. Linear from the word linear, continuous. So in linear regression, you can either have it as simple, practically, you can either have it as simple or multiple. Simple when you are taking each and every IV and testing it against the DV, then multiple when you combine a number of IVs into the system or model to control for any confounding. That's when we use multiple with linear. Then what about if the DV is categorical? If the DV is categorical, then there's another form of regression that you adopt, which is called logistic. So logistic regression is when you have a categorical DV. For example, you have disease occurrence or either yes or no, or you have something like health-related quality of life, where you can have poor or good. So anywhere you have a DV that is categorical and is not continuous, and then you want to predict or you want to check for the association between the IV and DV. So you conduct logistic. So there are different also types. If the DV is 2, then you go for binary logistic. If it is more than 2, multinomial logistic. But then generally, even the logistic can be simple or multiple based on the adjustment you want to make. You want to just check one by one, we call it simple. If you want to control for confounding, confounding is when one variable can influence the effect of the other variable. Then you go for multiple just to adjust. So this is another paper that I led. Here we are trying to identify the predictors of COVID-19 acceptance among university health science students in Nigeria. So I want to show us how we did the simple and then the multiple logistic regression. In the simple here, when we ran the analysis, we included each of the variables one after the other as against COVID-19 acceptance, as in each person must have given a response. So we want to compare that cumulative response as against the independent variables here. So normally you run simple regression, logistic here because we are dealing with categorical variables, to screen for possible inclusion in multivariable logistic regression. You just want to screen whether those independent variables are actually influencing the DV. So you want to check for age, gender, and any other variable that have one after the other just to check for any significance. So after you finish, after you check those ones that are significant, and then you want to adjust for any confounding, you put all of them in together to get what we call the adjusted model. So for example, here, before I leave, let me just interpret this. When you here we want to predict actually COVID-19 acceptance. So we have two different readings. We have the odds ratio, and then we have the p-value. P-value, like I explained earlier on, we have already set it at, for example, 0.05. So once the p-value is less than the set alpha level, then we say the statistic is significant. But then what is the strength? That's the advantage of regression. It will give you the strength of those associations. So how much impact is the DV upon the IV? Is the IV upon the DV? So here we can see that those participants that are age 25 and above, they are 1.77 times more likely to accept COVID-19 vaccine. You understand? That's just the interpretation. You have your reference as one, and then you compare the groupings. So also in the multiple logistic regression where you adjusted, we can see that those that are greater 25 years or older are 2.72 times more likely to accept COVID-19 vaccine compared to those that are having a smaller age. And the result is significant because the p-value is less than 0.05. So this is just the regression, different regression types. And then this another example from another paper that is being led by one of our very proficient scholar, Dr. Awal, where we looked at the predictors of knowledge of anti-snake venom in Nigeria, among health practitioners in Nigeria. So here I just presented the multiple logistic regression model. Already we must have conducted the simple logistic, and then the final model is presented here, where we have those that actually did not engage in previous training on anti-snake venom, they have 0.365 less likely chance of having knowledge. And it's practical. If you don't attend training, the chances of you having that knowledge is low. So not to still keep us just theory. We'll soon start the practical session. Before the practical session, we can have a short time to take some breath, and then we can set back and continue with the practical session. So these are just some future prospects or guides. If you want to learn statistics, you have to be actively engaged in it. It's not theory, it has to be practically done. But then for the theory, you can join a lot of courses. There is Coursera, under Coursera, Udemy, AI. AutoAid, yeah.
Right.
Then you can check publications. You can check some of our publications. Also check publications from top journals. Then practice, you can choose. It doesn't matter which statistical tool you are using. As basic, you can try to familiarize yourself with SPSS, which is just click, click, click. And then if you are good in giving command, you can go with Stata and R, which are more efficient. Then also currently with the advent of AI, you can be able to use AI, even though you still have to know the basics, because AI can be misleading. I've attempted several times, but then they can just give you idea. They cannot actually give you something that is very tangible. So it's just to have an idea. You can ask them, if I have this data, what kind of test should I go with? But then you still have to have the idea so that to confirm. These are just confirmatory platforms. You just want to confirm whether what you have seen or come across is actually true or not. Then recently I came across Julius AI. I have not actually used it, but then I've seen some feedback that it can also help in analyzing your data. So we take this short, like 1 or 2 minutes to take some breath, and then we come back to have some practical demonstration. But
Yes,
if you have any
thank
question,
you. Well.
we can
Thank you
take.
so much, Dr. Mustapha, for this amazing presentation. As we announced at the beginning, this presentation is going to be in two parts. The first part is more of like a theory to have a background knowledge about what the topic is all about. And the second session is like a more of like a hands-on. And thank you so much, Dr. Mustapha, because he has actually done very well. He has broken or he has explained very complicated technical terms into a simpler language that someone who is not versed in biostatistics will understand. And thank you so much. I know we have a lot to ask, but before going to the next session, I have two announcements. Number one, we would like to acknowledge the presence of Professor Danjuma from Professor Mohammed Danjuma, who is the director of Venom Antivenin and Natural Toxin Research Center at Ahmadu Bello University Zaria, and all other important personalities here at the webinar. And at the second thing I want to also share with us is, before going to the hands-on training, I want to share one of my slides, which is from my MSc Biostatistics class, which I'm sure will add more information to what you have just learned. And at the end, I'm going to send it together with the webinar slides into your slides so that you have good understanding of what Mustapha said. So this is not my slides, it's the slide from my MSc, from my teacher. It's just to explain further what Dr. Mustapha said, just to give us more understanding of. So I'm not going to give so much explanation. I'll just run through the slides. So it's a statistical test by Dr. Miet. Dr. Miet is my master's course supervisor. And so, like what Dr. Mustapha said, biostatistics, or anytime you conduct a research, you spend so much money, time, energy. But if you make a mistake in selecting biostatistical method, I can tell you end up wasting your money and time, because at the end, you come out with something that is rubbish. And at the end, you might not get any big journal to publish it. As you can see, the journals he shared, most of them, they are high impact journals, and most of them, they are Q1. Like the one for COVID information overload, it is the most cited paper in COVID information overload field, as I'm talking to you now. It has been cited by WHO, UNICEF, and many other big organizations to demonstrate information about COVID information. So if the biostatistical method is wrong, definitely do not even look at our paper. So I am advising us to really get this right on time, so that it will save us a lot of time and going up and front with journals. So if you are conducting univariate, like what he said, age and hypertension, they are 1-1. So these are the tests that you normally do. He has already explained it. I'll just go through the slides just to give you a summary of what he said in addition to his slide. It's just an additional information, and we are going to send this to your email. So you can see if you have independent variable, dependent variable, it is parametric, this test. If not parametric, this test. And then, so if you want to do a multiple, they do simple logistic regression. These are other conditions, has already been explained by Dr. Mustapha. It's just an additional explanation I said. All this has been said by Mustapha, so I'll just run through the slides. This one too, this all the explanation done, and this is the table. So if you have group A, group 2, and control, then measurement 1, if you have intervention, sample, then at the end, which test will you going to do? So if you want to compare this, then you have one way and over, this, one way and over. Like if you have two groups, then one way and over. If you have, so just an additional information I'm providing, repeated measures. Then as well, if you have independent t-test for non-numerical, independent t-test, independent t-test. So I'll just go through it without more details explanation. Just to have paired t-test. So if you know this logic, it will really save your time and energy while you are conducting research. And also, while you're at the beginning, when you have your conceptualize your research idea, you must consider both statistical tests to conduct, because that will help you that will guide you to statistical method, to the research method you're going to, the variables you are going to collect, and your outcome variable you are going to measure. From the first time you want to conduct research, you must know the best statistic method you want to use. And that's the reason why we need to have a proposal. So in the research proposal, you indicate which statistical method. So if there's any issues, you just be playing around your research proposal until you finalize which method you are going to use. So if you don't know much, or when you finalize, you can ask any expert in biostatistics, okay, this is what I have, this is what I propose, the statistical method. What do you think? Is it okay or not? So once you go through it and see the variables and outcome variables, then if you give you go ahead, then go ahead. If there's any issues, then he will let you know. And I'm very sure he will give you some papers to also go through and see which way to go. Like the paper he initially cited or showed, at PSI, we just think that there are so many things going wrong or not going right with most of the papers published from Nigeria, let me say this way, in terms of biostatistical. And we went through, and research was led by Dr. Abubakar Biyaminu, and we researched and we find out most of the papers, they don't use ANOVA rightly. And for some reason, the journals keep on publishing them. And this paper has been cited by so many research communities. So please, like I said, if you want to conduct biostatistical research, first get it right from day one, which biostatistical method you are going to use. If you make a mistake from the first time, you end up wasting your time, and possibly at the end, you'll be having so many rejections from journals, and they'll be blaming the reviewers are too harsh, are too this, they don't want publish your paper. So I'll send this slides to your emails. Please make sure that you click on that link, and please put your name and email address. Then we are going to send all the lecture materials to you. Thank you so much, Dr. Mustapha. You can write down.
All right, thank you so much, Dr. Abubakar Ibrahim Jato, for that short summary and appraisal. Yeah, I agree with you. Like you said, it is very important to start having your data analysis plan right from onset, because you already know your study design, you already have your proposal. So why not have include your statistical analysis plan, which can guide, especially when you are collecting the data or at the final stage of analysis. So it is important. Things may change, but then you still have to give some skeletal information that you intend to achieve in your research. So I would like us to take this few moments to appreciate the practical demonstration of the statistical analysis. There are quite a number of them, and for the purpose of time, and then for us to digest what we want to do properly. So we're just going to cite a few, and then subsequently we can be able to elaborate on others that we are unable to demonstrate today. So let me share my screen. Yeah. So I will be demonstrating to you some basic statistical tests that you can conduct using SPSS. SPSS is one of the, I think, most user-friendly statistical software that, even though it's not free, but the interface is quite friendly and you can be able to navigate easily around. So, and for a starter, I would strongly recommend that you acquaint yourself with it. And then subsequently, if you feel like there is need for you to take more advanced statistical softwares, you can go with starter. Starter is also very great. And then R as necessary. So during, just to give some general overview, like we said, the ingredient for every statistical analysis is data. So you first have to have the data. So the data, you have to collect it through experiment, through survey, depending on how you actually collect the data. And then you need to like clean the data if there are missing values or values that are not actually making sense, extreme values. After cleaning the data, then you can be able to then import it into SPSS. You can import, you can also copy and paste. There are different ways you can bring in the data into SPSS. So I would like to, this is the data in Excel, which I actually moved to into SPSS. It was just copy and paste. And then I can show you in SPSS what are the basic things that you should pay attention. So here the data, we have different variables. Some of the variables are in categorical format, some are in continuous format. So basically, SPSS has two interfaces. You understand? We have the data view and the variable view. The data view is what shows the individual subjects. Like each row here represent a subject, like one person or, yeah, individual. So like for this individual, it's serial number 1. This one is paracetamol treatment, whether the person takes paracetamol or not. This is the age of the same person, the gender of the same person, the educational level of the same person, the income. This is before, or temperature. This is just fictional data, so don't worry about it. It was just randomly created. So at the end of the day, even if we're getting something crazy, we shouldn't bother so much about it. It was so fictional and just generated for the purpose of illustration. So this is just temperature, pre and post. Then this stress level, 3 levels. Then this health-related quality of life. So this is what is obtainable in the data view. Then in the variable view, this is where you can define what actually your variables are. For example, here we have the paracetamol treatment, we have the age, the gender, the education, and so forth. So also you have to define the variables. Like, for example, paracetamol treatment. We coded the paracetamol treatment as 1 and 2. Here you just add. Let me just reset and do it again. Reset or remove. Sorry. So here you can be able to add your, what do you call it? You can actually remove all of them. Yeah. So if you want to define the treatment, whether the person has taken paracetamol or not, we have already predefined it here in the Excel. Already, whenever you collect data, the data should actually be numerical for you to bring it into SPSS, preferably. If you allow it to be reading something like gender here, so at the end of the day, you may have some string that you may not be able to analyze properly. So what I advise is whenever you collect your data, try to code them, you understand, based on numbers. So those numbers, you have them like, you have like where you use the keys, like paracetamol, whether the person has taken paracetamol, yes, gender, whether male or female, 1 and 2. Education, whether the person is having diploma, undergraduate or postgraduate. Health-related quality of life, whether it's good or poor. These are what we call the categorical variables. So you code them so as to be suitable for importing into SPSS. So like we have for paracetamol, we said yes is 1. If they have taken paracetamol, sorry, if the value is 1, the label is yes. Then we have 2, no paracetamol. So as simple as this. So whatever categorical value you are bringing, you use this value option to describe what the numbers are. For male, we have 1 and 2. And then for education, which is in 3 levels, we have 1 as diploma, 2 as undergraduate, 3 as postgraduate. So another thing that is also very important here is the measure. So what is the level of measurement? That's when we talk about whether the data is categorical or numerical. And we said for the categorical, we have 2 different ways. Either it's nominal without order, or it is with order. So you can see these 2 are categorical. Then if it is continuous, SPSS use scale to describe both ratio and interval values. So you just use scale. So like here we have paracetamol treatment. You believe with me that it's categorical because it's 1 and 2. That's why we choose nominal. For age, because it's continuous, no need to add any value. So we use scale to represent it as continuous. Later, you can decide to upgrade the age. Probably you are interested in grouping the age into 2, maybe less than 20, more than 20. Then when you do that, you have to change the scale to nominal, because now you are grouping them. But as it is now, you leave it as continuous. So the same thing with gender, education, income, and then health-related quality of life, which is also categorical. This one, because it's temperature is continuous, so we put it as skill. So these are, for me, basically just what you need to touch and nothing more. And then you also have to familiarize yourself with this, what do you call it? The top icons. These icons are where you do your analysis with. You click and then run the analysis with. So remember we talk about univariate analysis, the descriptives that we talk about, the mean, the median, the standard deviation or interquartile range, and then of course frequency and percentage. So if you want to, for example, if we take paracetamol, treatment with paracetamol, you can see that treatment with paracetamol is actually categorical. So the correct statistics to describe this type of data is frequency and percentage and nothing more. So there are 2 ways. It's either you go to analyze, you go to descriptives, not even 2 ways, many ways, but I will just show you a few. So you go to descriptives, you go to frequency, and then you just move your paracetamol treatment. Under statistics, no need to click anything because you are just interested in the proportions, and then you just click OK. So the output, this another interface, which is the output of the SPSS, where whatever analysis you do will be presented here. So this is the summary of what analysis you are conducting. So we can see that this is a snapshot of actually the distribution of whether the subject takes paracetamol or did not take paracetamol. Those that take, we have 45% of them, and those that did not take, we have 55% of them. For frequency, we have 9 and 11. So basically, this can give you an idea about the initial summary statistics of the data set. For example, if we're dealing with continuous variable like age, So definitely we are not interested in mean, median, sorry, we are not interested in percentage or frequency. Though in some instances we may be interested in that, but generally you would just want to know what are the summary in terms of mean, median, mode, standard deviation, standard error, as the case may be. So also this, you go to the same icon, you just go to analyze, descriptive statistics, frequency, and then this time around you put age, but then you still have to ensure that you click the relevant summary statistics that you are interested in. Like here we are choosing mean, median, mode. You can choose your standard deviation, variance, the minimum, the maximum, standard error. So all this will give you like a general summary of what is the mean value, what is the standard deviation, what is the median, mode, as the case may be. Yeah, so here you can see that this is the summary statistics. We have the mean age to be 32. We have the standard error to be 1.08, the median 31, the mode 30, the standard deviation 4.8, the variance is there, the range is there, minimum and maximum. So you can note the difference between continuous summary of a continuous variable and a summary of categorical variable, which I demonstrate to you in some of the previous publications that we had. So now, having known that, then the inferential statistics, now we want to do the hypothesis testing that we are talking about. We want to check whether there is any significant difference. If we are looking at categorical, whether in proportion, is there any difference in proportion between two groups? Like last time from our, what do you call it? This summary table, we say if we're looking at one sample, then one sample t-test, two sample, uh, depending on whether it is paired or unpaired t-test and paired t-test. So this is exactly what I want to demonstrate to you now. So for example, we want to conduct, we want to look at a parametric test to compare the differences in, let's say, income between age groups. Let's say we are just comparing, is there any significant difference between the income of male and female? So male and female, two levels, and then income is continuous. Okay, lest I forget, there is what we call normality test, right? So ideally, we are supposed to at least look at and check whether these continuous values are actually normally distributed or not. Even though we have a very small sample, about 20, so the chances that this data is normally distributed is very slim. So how do we check the distribution of the data? I think I should start with that. So you go to analyze, and then you go to descriptives, then you go to crosstab. Let's say, for example, we want to check that of age. Okay, I think we are going to go to explore. Then we take age. Yeah, this is normality plot test. This is actually where you check the normality of your data. So you go to analyze, let me go again. You go to analyze, you go to descriptives, then you go to explore. So, and then you take your, you can do all these scale variables, you can just put all of them just to do them at a time. It will not affect the other. So you just go to plot and you just click normality plot with test. So here it can show you whether the data is normally distributed or not. If you want, you can click histogram, but let's maintain the normality test, which I will show you how it looks like now. So this is the output. I think it's still running in the background. Yeah. for normally don't worry too much about all the output that it's bringing. Just focus more on what you actually looking at. For example, here we have age. This is just the same descriptive statistics that we check for age. But what is more important when it comes to normality is these last two items, the skewness and ketosis. So skewness, we want our data not to be skewed. It should be like normally distributed, having a dumbbell shape uh, format. And then for ketosis also, we want our data to also have maintained the same shape. Ketosis is when it is too deep or or it spikes. You understand? It can go down, it can go up. While skewness, it can go left and right. So, but another thing that is important is the normality test, which is here. We have two different tests of normality. We have Kolmogorov-Smirnov and we have Shapiro-Wilk. So these two tests can be differentiated based on the sample size. If the sample size is small, then you go for Shapiro-Wilk. If the sample size is big, then you go for Kolmogorov-Smirnov. You can see we all have only 20, and I think 20 should not be big enough. But whichever one, sometimes there is no any actual definitive way to go about this. It's just based on how you can be able to justify. So let's say we believe our sample size is small because it should have been bigger than that. So Shapiro-Wilk, then we check for the significance. For example, if we are taking age, the p-value here is 0.995. Remember, we said we are setting the alpha as 0.5 conventionally. So we are having a p-value this time around that is greater than 0.05. So when we have this, we say that the data is not normally distributed. It's like the reverse of the normal statistical test we do. For normality test, it goes like in the inverse direction. Instead of saying that if the value is greater than 0.05 to be not normally distributed, this time around we say that, yeah, the value is not normally distributed because it's having, it's normally distributed because it's having a p-value that is greater than 0.05. So like, for example, if we look at temperature, temperature is 0.005. So we don't want to see significance in the test of normality. So meaning when we have any value that is less than 0.05, then the data is not normally distributed. You understand? Which is this. So for temperature is not normally distributed. Stress level of 2 is also less than 0.05, is also not normally distributed. But every other thing, because they are greater than 0.05, we believe they are normally distributed. So at least we have some lack of normality in our data. But then I would try to ignore that and just demonstrate as if our data is normally distributed. So if our data is normally distributed and we want to conduct the simplest test, which is, for example, one sample t-test. So if we want to conduct one sample t-test, we go to analyze, we go to compare means, and then we take age, for example, as the dependent variable. You don't have to click anything on the option. Sorry. We go to compare means, sample t-test. Yeah, yes, you put age, and then you set, normally in one sample t-test, you should have an idea what kind of value or variability you are looking at. You should have some kind of arbitrary number that you want to compare the test with. For example, this, we have like ages around 23, 30, 35. So let's say, for example, we are setting the estimate as 25. So you have an arbitrary value that you want to compare your age with. So you just say, okay, and then you check the results. The result is presented here for each. There are quite a lot of jargons. Don't worry about it. The most important thing that you need to focus is your level of significance, which your p-value, sorry. We have here two-sided p-values. Two-sided is when you have a decision that can fall in both directions. It can either be an increase or decrease, so you are neutral. But then if you are taking one-sided, so you, right from your hypothesis, you are saying that the value should increase. We are taking a side. So for now, since we are not taking a side, so you go with the two-sided. So you can see that the value is significant, meaning the mean value that we calculate is significantly different from the arbitrary mean that we imputed, and the difference is statistically significant. So this is one sample t-test. Let's take, say, for example, we are conducting independent sample t-test. You go to analyze, you go to compare mean, you go to independent sample t-test, and then, okay, let's say, for example, our test variable, because using age as a test variable may not make actual sense. Let's maintain it as the independent variable. And let's say, for example, we want to check based on gender. Gender has two categories. Yeah, this will be a very perfect example. So we want to check if there's any differences in income. Any continuous value can go into the outcome variable for demonstration's sake, but everything lies on your research question, your hypothesis, but this one is just a general demonstration. So don't worry about us mixing the different variables, even if it doesn't actually make sense. So let's say, for example, we are looking at age, and the age we have already from that coding is 1 and 2. 1 is male, 2 is female, so you put it as such. And then let's say, for example, let's still use the age or income. Let's use income. We want to see if there is any significant difference between male and female regarding the income, whether males are having statistically higher income than females or not. So you just take the two variables and then put them, the grouping should be the gender, where you have two levels. And then this one must always be continuous because we are dealing with a parametric test. Then you said, okay. So also here you try to focus on the main table, which is this independent sample t-test. Yeah. So you want to check on the test itself. You understand? The test itself, let's use the two-sided because we are not sure of the exact direction. Even though when we check the summary statistic, we can be able to see which one is higher than the other. So like here, we can see that when equal variances are assumed, which is basically one of the most common one that you should choose, then the p-value here is 0.002. So what does this mean? It means that there is actually a statistical significant difference of the income when you compare male and female. So if you check the summary statistics, you can see that the income of female is 60,000, and then is it 60? Yeah, 60,000, and then that of male is 43. So meaning females are having statistically higher income than males. This is just what this p-value is talking about, because it's less than 0.505. And then when you compare the two means, you can actually see that, yeah, females are having a statistically higher income compared to those that are male. So normally you just take your summary statistics. I advise not to copy paste because I noticed some reports, you just copy the output of SPSS and paste. Try to generate your own table yourself so that to make it more aesthetic. So you just transfer the mean values and the standard deviation into your table, and then you can use asterisks. You can report the p-value of 0.02 on your table. You can also decide to report your confidence interval. Confidence intervals sometimes are also even more precise compared to using p-value, even though they can give you an idea of whether the test is statistically significant or not. If you are looking at the confidence interval for a test to be statistically significant, you want to ensure that there is no 1 in between. So you can see that here we are having -27 to -69. So definitely 1 is out of it. So this is independent sample t-test. For example, if these two data are paired, they are dependent, they are connected in some ways. So we use paired t-test. Paired t-test is also here. So you go to paired t-test and then you put your variables. For example, we are looking at pre and then post temperature, the temperature before and after. So here we just say, okay, we want to check overall whether there is significant difference between the temperature, the average temperature reading before or after the treatment. You can see the average is 38 and pre, and then post we have 37. So then we check our p-value to confirm whether the difference in those two means are statistically different or not. So you can see that the p-value here is less than 0.05. So meaning there is a statistical difference between the pre-temperature compared to the post-temperature. Pre-temperature is statistically higher. When you look at it, you may want to conclude that there is no difference, but statistics know what it does at the back end to bring out something that makes more scientific sense. So then we can go for ANOVA. ANOVA, that just like we said, a lot of Nigerian scholars, they misuse ANOVA. So after today, I want to believe that we should not be found wanting in misusing ANOVA. So ANOVA, we also dealing with continuous dependent variable and then more than 2 levels of groups. So we go to compare means, we go to ANOVA. Which parameter has more than 2 levels? Let's say education. Education has diploma, undergraduate and postgraduate. And let's say, for example, we're checking for stress. We want to see whether diploma are having more stress compared to undergraduates and postgraduates, or the other way around. So I will not conduct post-hoc test. I will tell you why, but then we can do it for demonstration purpose. But first, you just check the general ANOVA just to see if there is any significant results. So we run the ANOVA. You can see that the ANOVA is statistically showing statistical significance. The p-value here is actually less than alpha. So definitely there is a difference between the the mean stress scores. The scores for the stress levels actually differ, at least in one of the combination, whether diploma are having more stress than undergraduate, whether they are having more stress than postgraduate, but we actually don't know where that difference lies. So that's when the issue of post-hoc test come about. Remember the papers that I showed you, one used DUNET because we want to fix one as reference and then compare every other to that reference. But then if you just want to do a family-wise kind of comparison, irrespective of the peers, then you go for other tests. I will show you now. So what we do now is just simple ANOVA, but then we don't know where the difference lies. So you come to post-hoc, you go through the same process. This time around, you come to post-hoc. Then you have quite a lot of post-hoc tests that you can conduct. If we want to fix one, maybe we want to fix diploma and then compare every other options with diploma, then we use DONET. The limitation of DONET, you have to fix one. It's either you are comparing with the last option or you are comparing with the first option. First option is diploma, and then last option is postgraduate. So it depends on the study design. But then when you conduct family-wise comparison, even the DONET will be part of the multiple kind of comparison. So there are different tests, but the common one is Bonferroni. There is also 2K. Let's adopt one. All of them, they are a bit reliable. Whichever one you use is still correct. Sometimes people want to force their results to be statistically significant, so they play around with all this kind of post-hoc tests. But as far as I'm concerned, anyone you use should be fine. So let's say we are taking Bonferroni, for example, to find where the actual difference lies in the differences in means. So after the multiple pairwise comparisons, so we can be able to check where are actually the difference. You can see that, yeah, undergraduates and postgraduates are showing statistical significance. The p-value here is less than 0.05. Sometimes you will see asterisks like this just to prompt you to know that, yeah, there is actually a difference. So how do you know the difference? You go back to your mean. You have to conduct mean to be able to see whether those that are having undergraduates are having lower stress level compared to postgraduate, or is the other way around. So this you have to check the mean values. And how do we check the mean values? You just go simply to, I'm not sure whether in ANOVA we can be able to, yeah, you can still in the same interface, you can just click descriptives. There you can be able to see the actual values, then you can easily make the interpretation of the significance better. So here we can see that the mean for stress level for diploma is 53, 47 for undergraduate, and 57. But then our finding is that there is a significant difference between postgraduates and undergraduate. So postgraduate and undergraduate. So here you can see 47 and 55. So there is actually a significant increase in the stress level among postgraduate students compared to those that are undergraduate. So, or the other way around, statistical significant decrease in stress level in the categories that are undergraduates compared to postgraduates. So this is just how to interpret it. You have to get the summary statistics, and then you can report the p-values and use the respective annotations. So, for example, if we have we want to check, we checked last time and then we found out that our data is not normally distributed. And then we want to conduct a non-parametric equivalent of independent sample t-test. So you go to analyze, you go to non-parametric. There are two options. You can decide to use this initial choices, or you can decide to go to legacy dialog. If you use these initial choices, it will automatically pick the right statistics for you. But here you have to be specific. You have to choose how many levels do you have? Do you have 1 or 2 or 3 groups? So for example, if we want to be specific, we want to conduct Mann-Whitney test. We want to check whether there is difference between the mean values of a data that we believe is not normally distributed. Then we can go there to conduct Mann-Whitney U test. So also you identify your grouping, a parameter or variable that is categorical. For example, we take age, which is 2 levels, and then we check, for example, the stress level. So under options, you can check for descriptive statistics. Mark you, when you are conducting non-parametric test, it's better to report the median, because in most cases, in the usual case, for example, the median is actually what is being used to differentiate between the two groups. So we said, okay, then we can check the asymptotic significance, which is 0.255. So from this, our inference is that there is no statistical difference between the median this time around, because we are running non-parametric tests. So the median of both genders, male and female, there is no difference. We're saying that is the same. So if we have more than two levels, two groups, we run what we call Kruskal-Wallis, the same way you go to parametric, legacy dialogue. Instead of two independent, then we go for K independent. K independent, you can see Kruskal-Wallis here. So like which value has more than three levels? We have education, and then we have the minimum as 1, the maximum as 3. And then, for example, we are also checking their differences in the median values of their stress level. We can click the descriptives, even though the descriptives is showing mean, but you can always click median. You see median here to get the median value. So you say, okay, and then you check the significance. You can see that, yeah, according to our statistic, Kruskal-Wallis is saying that among the three groups, there is at least a difference in the median stress level. Among the three groups, diploma, undergraduate, and postgraduate, there is actually at least one group is either bigger or smaller than the other. So we don't actually know where that difference lies. Then, of course, we have to conduct what do you call it? We have to conduct a stock test. Unfortunately, Kruskal-Wallis doesn't have where we can just click to do the post-hoc test. Then you have to go back and conduct pair-wise comparison with Mann-Whitney U-test to see where the difference lies. So you just have to be checking them one after the other to check for the difference. So this is Kruskal-Wallis, and then regression. Yeah, let's touch regression because I cited example. From the data, if we are interested in predicting one of the variables based on some of the other variables, we call the predictors the independent variables. Then we call the outcome, the dependent variable. For example, we want to predict stress. We want to find out what are the factors, whether age, gender, education, that could predict or is associated with stress. So what we do here, we go to analyze, and then most importantly, the stress is continuous value. So we are using continuous type of test, which is linear regression. So you go to regression, you go to linear, and then we are moving our dependent variable, which is stress level, which is continuous. And then remember I told you we have what we call simple linear regression and multiple. Simple is when you are taking the individual variables and be running them one after the other. And then multiple when you combine a number of independent variables to actually correct for confounding. So let's say we are starting with the simple linear regression, sometimes because we want to ensure that we have the right output, you can click on the confidence interval, because the confidence interval should be able to generate the level of significance for this test. And then you just say, okay. So this is just the model for the linear regression for age. We want to see if, what do you call it? Age can be able to predict stress. So from the significance, we can see that, yeah, the output is statistically significant, meaning, yes, age can actually predict stress, or age is associated with stress. So to what extent, that's where we check the beta. Yeah. So from the beta, you can see a negative. Anytime we have a negative, meaning it's on the inverse direction, like increasing age is associated with less stress, as simple as that. As you, with 1 unit increase in age, your stress level will decrease by uh, 0.67. You can actually convert it to percentage. Just say this value -1. It will give you the percentage, and you can describe it like that. So let's say, for example, we are using age, for example, instead of gender, and we are using gender instead of age. Then for gender, remember, we have 1 and 2. So probably we are using 1 as reference, and then 2, which is female, as the test. So here we can see that the p-value is showing no difference because it's greater than 0.05. So even if we have any effect, like we can see the effect size, because it's not statistically significant, we cannot actually make any judgment. So, and then if we are to conduct multiple, just to control for confounding variables, confounders, so we can put as many variables that we think are likely to be associated with stress and check them. So when we do this, we have different options. It's either we check enter, or we use backward, forward. So it all depends also on our choice. Enter will force all the independent variables in the model. It will not remove anyone. While if we click backward or forward, any parameter, any variable that is not significant, the model will just remove it. So let's say, for example, we're using backward so that we want to just get rid of those that are not significant. You come to the final model. Yeah, so it will run a lot of statistics around. So just focus on what is shown at the last step. So step 3, we can see that age is still retained, while gender and education were removed. And we can see that it's statistically significant. So at the end of the day, when you are reporting your final model for the multiple regression, this is actually what you will report, because every other thing is removed. So last but not the least, let me just demonstrate logistic regression, which is just very close to the linear regression. So in logistic, you go to regression where you have a categorical outcome. You go to, for example, if the outcome is binary, let's say we are looking at the differences, the health-related quality of life, which has poor and good. We want to predict what are the variables that can predict or associated with health-related quality of life. So dependent variable would be our health-related quality of life in 2 levels, poor and good. And then we want to see one after the other. That's simple logistic regression. If there is any value that can actually predict our outcome, which is health-related quality on its own. So we also go and take our confidence interval. Sometimes I try as much as possible to create classification plots, because it will actually tell me the direction in which the prediction is going. So I click the classification plot and I just say, okay. So let me just go to the classification plot. We said the predicted probability is membership of poor. So meaning we are predicting those with poor health-related quality of life. Then we go to our model and check whether we have statistical significance. So meaning here, age is not a predictor of poor health-related quality of life because it's not statistically significant. Then let's check another value. Let's say we are using gender. So if you put categorical value, then you have to define what will be your reference. By default, the first is your reference. First is male and the second is female. So we can leave it as first. Just take note of it, especially when it comes to interpretation. So we click continue and then we just say okay. So we are predicting membership of poor. What are the factors that can predict poor health-related quality of life? From the significance level, we can see we don't have any association because it's significant. So definitely gender, age, they are not predictors of health-related quality in this fictional data. You understand? So this is just everything is fictional. So don't assume that we are making any conclusion from this demonstration. So I think the last one that I've not demonstrated is chi-square. Chi-square is also another test where we want to see any association or differences in proportion this time around. So to conduct chi-square, you go back to the descriptive statistics table, and then this time around, you just click crosstab. So in crosstab, normally row, we put our dependent variable. Let's say, for example, we are trying to compare the differences in proportion between, or any association between gender and level of education. So let's say we are putting education as row and then gender as column. Here, exact, especially like last time I told you, there is Fisher's exact test, but it will automatically run it. No need to even tick anything. So for the statistics, you click chi-square. I think chi-square is only relevant. Then for the percentages, we want to have an idea about the row percentages. We want to see the distribution of age in the, of gender in education, across educational levels. So we just say, okay, it will bring the p-value for the chi-square, which is popularly known as Pearson's chi-square. And then you check the asymptotic significance, and we can see that it's not significant. So meaning there is no any association between gender and level of education. So this is actually a simple and basic demonstration of statistical analysis using SPSS. Like I told you, there are many, many tests you can conduct, but for the purpose of today's discussion, we are limiting it, and because of time, to just a very few illustrations. So I would like to thank you all for listening. I hope that this small discussion would have at least changed some of the perspective that we have, even though I know it's going to be gradual. There are actually experts in the group, like Jato is very excellent in statistics. So, but I believe there are those that are just catching up, and this discussion today should be able to at least open our horizon and ensure that we are actually doing the right thing when it comes to analyzing our data. So I would like to hand over the podium to, I don't know whether Dr. Biliamin or Basira.
All right, I think I'll continue. Thank you so much, Dr. Mustapha, for this very wonderful and insightful webinar and hands-on and everything. And I'm so happy that you have condensed almost half a semester presentation in just 2 hours. And I'm so happy how you also break most of the statistical terms into non-biostatistical professionals. Yes, and also how you're able to run some of the tests in simple terms. Thank you so much. And before going to the questions, though I couldn't find any question on the chat box. Just a reminder that please, whenever you are trying to or planning a research, especially public health related research or any research that deal with data, I strongly suggest that you think about the Bell statistical method you are going to apply, because knowing it from the beginning will inform you which variables you are collecting and what outcome variable you are actually collecting and what is that outcome variable. Because many people made a mistake of even number one, even identifying what is my outcome variable. Because knowing outcome variable, number one, and knowing the classification of that outcome variable, whether it is numerical or categorical, is another problem. And having it categorical, numerical, then how to measure it, that's another issue. So first, identify what are you measuring. Let me give you an example, like knowledge of high blood pressure in the community. So when you say knowledge, there are two things. You can say, okay, they have knowledge, which is yes. They don't have knowledge, which is no. So this is categorical. So knowing it as a categorical is the first step. Then how many levels? Yes, no, mean 2 levels, mean binary. So when you are reading that table by Mustapha or that chart, so it will now tell you where you are going. Categorical, yes. 2 level, yes. So this is what I'm going to do. This is the test I'm going to test. Then also, if you want to say, okay, knowledge, you want to say, okay, 20% have knowledge, or the knowledge is 30%, 20%, that is numerical. Or maybe they have, okay, the knowledge score, they have 10 score. If you take it by 10 or by 100, they have 30 score. So this is what you call numerical. You take it by numbers. So then you now have to go, okay, you want to compare the score between those in the between year 1 student and year 2 student. Then you now know which statistical method you are going to use. Also, the same score, the same knowledge, you can categorize it into high, medium, and poor. That is ordinal, into an order. Higher, medium, low. Of those who score first, second, and third, like you categorize, given a rank. Even that one will now know which statistical method you are going to use to analyze this. So knowing this will actually give you an idea where you are going to really save you time. Like this, and like I think the guys are listening, they are part of this participants. So there's a research we are doing, and from the beginning, and any statistician, once you see the title, to give you an idea, the statistical method you are expected to see in the main, and that's what most of the editors and the reviewers are doing. From the title, we think, okay, this is what we are expected to see. So when we see from the methods and results, you are measuring something that is entirely different from what you collected. So definitely there is no need to even go through reviewing your paper. It's automatic rejection. So once, assuming high blood pressure, yes, there is blood pressure. No, there's no blood pressure. And you are now trying to measure mean, or you might mean of, category, yes, no. Mean is different. So you have to use any statistical that measure categorical variables. Yes, blood pressure, you can use numerical when you take the numbers, like they have 120/80, like in numbers. But when you categorize it as there's blood pressure, there's no blood pressure, or yes or no, then definitely it's categorical. So I've shared some resources on the chat box. That's because if you miss the basic ball statistic, all this thing that Mohammed spent 2 hours is explaining, you might not understand it. But if you know the basics, categorical variable, numerical variables, then it will give you because even if it's numerical variable, if you do the test that Mustapha did, that's normal distribution. It's not normally distributed. You can't proceed with the numerical test. Like what you say in ANOVA, if it's non-normally distributed, you can't proceed to ANOVA. One of the main key requirements for ANOVA is to have normally distributed variable. And if it's not normally distributed, you can't proceed. You have to use other statistical criteria, which you explained. So number one take-home message is, number one, to know the basic bulk statistical terminologies, to know the variable, to first know what is your outcome variable, knowledge, yes, knowledge, no knowledge. Then to know which bulk statistical test you would employ for the test, the outcome variable you are testing, and then taking the fulfillment to see have they all fulfilled all the requirements, then you go ahead and do it. So once you have this, and then I don't think you have any problem for anything. Let me hand over to Dr. Basira Kenkia to give the closing remarks and presentation of certificates. And I can see some questions from the chat box, and I think I'll just go through them now. If your data is not normally distributed from normality test, how can you solve the issue if you want to conduct parametric test? So Dr. Mustapha, you know this one, and then yes, we are going to send all the recording to your emails, and I think that's the only question we have. Question from Dr. A.S. Wada. Is presentation of results as mean and standard error or mean standard deviation dependent on statistical method or by choice? So I mean, what he's saying that if you're presenting a mean, is mean standard deviation or mean standard error mean? Which one is it, by choice or by requirement of statistical analysis? Another one, I'm just reading, then you can take note of them and answer them. Yes, we are going to share the link. Yes, I think that is what we have for now. Then if you have any other question you want to ask, kindly raise up your hand, then we recognize you. And then, yeah, someone said, I need more explanation on two-sided p-value. All right, over to you, Dr. Mustapha.
Okay, thank you so much, Dr. Ibrahim Jato. I believe you have already summarized again what we have discussed for these 2 hours. So just to go straight to the questions, there is a question regarding if the data is not normally distributed, how do you conduct a normality test? So yeah, like I said previously, whenever you are conducting the test, you have to check all those assumptions. So, and then fortunately or unfortunately, your data happens to be not normally distributed. You have a choice whether to conduct a non-parametric equivalent of the test of interest because your data is not normally distributed. That's one. Then secondly, you have another choice to convert your data, especially if the data is continuous, to convert it into what they call log form. If you log transform your data, you can be able to convert it, and if you check, it will be normally distributed. But the thing is, anytime you are moving from one what do you call modification to the other, you are actually reducing the power. You understand? So if you have your data that is not normally distributed and you are log transforming it, you are actually reducing the power of that data. So at the end of the day, even if there is supposed to be a difference within that data, you may end up not having or seeing a difference. So you have options. Just go for either non-parametric test or log convert your data and do the parametric test accordingly. Then the second question is regarding two-sided p-value. Yeah, remember when I was talking about the hypothesis testing, I said we have a null hypothesis that actually say no difference. Then we have the alternate hypothesis that said there is difference. So that difference that you said in the alternate hypothesis, we are not sure of the direction. We don't know whether the direction is increasing or decreasing. So when you come to the test statistical test, especially when you don't want to fix the direction of the inference. You don't want to say whether it's increase or decrease, though later you can be able to see that. But then using the two-sided will actually balance the direction. So even if at the end of the day, you are taking a particular direction, but the p-value that is neutral, having that two-sided will not will make it a bit more balanced. So that's regarding the two-sided p-value. Then there is also whether representation of mean should go with standard error of mean or it should go with standard deviation. Actually, I may not directly tell you something very rigid, but I want to believe that it all depends on the researcher, because these two values are different. Standard error of mean is different from standard deviation. Standard deviation is talking about the variability within your sample. You know, whenever you are conducting a study, you must have taken a sample from a general population. So now you are forgetting about the general population. You are concentrating on your sample, and then you want to see the variability within that your sample of study. Then if you come to standard error, you are assuming that you are extending that finding to the wider population. So to what extent will that finding differ in the main or bigger population? So it all depends on you. But in most of our survey research, we use standard deviation. But I noticed people that do experimental studies, they report standard error of mean, even though I have no idea where their general population comes from, especially when you are dealing with homogeneous animals, because animals are believed to be homogeneous, while humans are highly heterogeneous. So I think the researcher or scientist can decide and then justify accordingly. So I think that those are the three questions, but I saw some hands raised. I want to believe they have questions. So Dr. Jato, can we unmute them?
Yes, Adam A. Umar.
Thank you very much, Dr. Jato. My name is Dr. Adam Umar from the Department of Statistics here in ABU Zaria. First of all, I just want to commend the excellent presentation by the presenter. He has done justice to the topic, because I couldn't imagine how a pharmacist become a statistician. He has done well for the presentation. I really appreciate his effort. Secondly, during the process of the presentation, at the analysis, at the practical section, he made mention about the large sample size, where he mentioned that sometime maybe if we're interested maybe in the testing the normality, we consider the either Kolmogorov or the other side, and this depends on the sample size. But he mentioned that, oh, it's not, maybe it doesn't matter. To us statisticians, it really matters, because for the sample size, we have some scientific, statistically, we have some basic of considering a sample to be a large sample or a small sample. So for the basic statistical analysis, when the sample size is greater than 30, we consider that as a large sample. And if it's less than 30, we consider it as a small sample. At least the idea is, or the basic idea, the basic idea here is that at least when we have 30 data points, these are enough information to make an inference. At least we can make some inference if we have at least a 30 data points. So just in brief is, when we have any data that is greater than or equal to 30, that is considered as a large sample size. And then in addition to the output, he makes so many emphasis on the p-value as one of the important value of interest when making the statistical inference or or comparisons. Yeah, of course, the p-value is the one of the important thing, but we should put it in mind, the other outputs are also important. So most of in most of the cases, we focus on the p-value, but the other output are very, very relevant in making any statistical inference. So we should try as much as possible to understand more of the interpretation of the additional of the other output of the value, not only the p-value. So the p-value is the most important thing. This is just two things I wanted to add to the presentation. And as I shared, he really make a good job. And thank you very much. I wish you best of luck. Thank you.
All right, thank you so much, Mr. Adomi Umar from Ahmadu Bello University Zaria, Department of Faculty of Biostatistics. Yeah, and his observations were very valid. And thank you so much, sir. We really appreciate. Do you have any other?
Let me chip in. Yeah.
Yes.
Thank you so much. I'm happy that you are here. So sorry for intruding into your territory. Actually, Dr. Umar is one of my very good friends. We have been together for many years, and I can attest to his exceptional qualities when it comes to he's already a statistician. So, of course, he has a lot of knowledge. And yeah, I agree that whenever we are discussing normality, the sample size is very critical. And I also agree that using a cutoff of 30 less than 30, we can say that is small and may likely not be normally distributed. Greater than 30 is good enough. So just to also add in, now I'm talking about when we have a data that is even, for example, 1,000, you understand? So when we have a data that is big enough, sometimes even if you check the normality, data is not normally distributed. Irrespective, there is this central theorem.
Limit theorem, yeah.
That mentioned that the bigger the data, the chances, even if the data you check is not normally distributed, you can look the other way around and conduct parametric tests. I think that was what I was just trying to emphasize there. So when you have a larger sample, even if the normality test is not showing something good, you can still proceed with parametric because it's more powerful. Then, yeah, I agree also with him that paying attention to other parameters in the output, apart from p-value, is very important. Yeah, we have the effect size, especially, for example, when we're demonstrating the regression. Of course, we cannot forget to use our odds ratio or beta. Beta is actually what was presented, but in the interpretation, you use odds ratio or relative risk ratio, depending on the study design. And of course, you have confidence interval. Sometimes confidence interval also very important because it goes side by side with the p-value, and it will show you that range to which that your test statistic falls. So thank you so much, Dr. Umar.
Yes,
I really
thank you so
appreciate
much,
your presence.
Dr. Umar. And
maybe we will invite Umar also because I believe he has a lot to share.
Seriously. Yes, so I'm Mr. Umar.
On behalf of Umar, yeah, really.
Yeah, I'll just ask him because our previous presentation, most of the participants were asking if we can have a session on hands-on training on using R. So I don't know if Dr. Umar will have time. We can arrange a special class to show us how to use R software statistics. That's when you are dealing big data. But anyway, we discuss outside this webinar to discuss more appropriate topic, and we share it to our normal route of reaching out. And just before asking, just an addition to just 1 minute or 1 second, addition to the ongoing discussion, I think currently there is like debate in the academic community about whether using confidence intervals or p-value while we are deciding about statistical significance. So yeah, so like you said, you might not always use the p-value. There are some other, or we cannot always rely on it. Like my supervisor, he always look at the confidence interval, even if it is significant. Once it's too wide, he always ignore it. And this is one of my trick when reviewing Global Burden of Disease Network papers. Whenever I see wide confidence interval margin, I always tell them the author should note that there is there is need for caution in interpreting the result because the confidence interval is too wide, despite that the confidence interval is significant. Anyway, I'll ask Dr. Olan. Sorry if I didn't pronounce your name very correctly, Dr. Ola. If you have time to say something, otherwise I can just jump to Dr. Mohammed Sagir, Mustapha to say something. Then we'll invite Dr. Kankia to give the closing remark, present the certificate, and call it a day. Dr. Sagir, if you are there.
All right.
Yes, sir.
Hello.
Yes.
This is Dr. Abubakar Biliamin. I just wanted to send my apology. I don't know if it's okay for me to speak now or.
Yes, sir. Your apology accepted, sir. Don't worry, sir. We have.
Okay.
Yes, sir. Everything is under control, sir. Thank you so much.
All right. Thank you.
All right, no worries. Dr. Sagir, are you close?
All right. Yeah. All right, Prof. Regarding my question is regarding the sample size. We are into experimental science using animals. Prof. Mustapha mentioned that the animals are homogeneous. Unlike humans, they're heterogeneous. Is it Dr. I wouldn't know is it Dr. Umar or who
Umar
tried to Dr. Umar. Please, can he present to us any journal that back that? Because like in my own case, I use my animals that I use in my study are less than 30. Hello?
Okay, yeah, we can listen. Yeah, we are hearing. Yes, so Dr. Mustapha, are you listening?
I think we are still talking about the same thing regarding the differences between human studies and animal studies. So human studies, the variability is very wide. Like you cannot, even between twins, identical twins, sometimes you can have a lot of differences. But for animals which are within the same environment, bred under the same condition, eat the same meal, they don't move around and get into contact with any environmental factor that change some of their characteristics. So we believe that even the smallest sample size that you will be conducting on animals should be able to give you appropriate results when you use parametric test. And it's very common that you cannot be using 100 animals for a research. You understand? So the few you use like 10, 20, 30, I believe because of that homogeneous nature. So using a parametric test should be able to give you the right inferences or right outputs for parametric test. But I believe this is science. There are a lot of things that could be going on relating to that. I have seen articles that are experimental that have actually used non-parametric tests. So I believe we can always have it both ways, depending on how we look at it.
All right, thank you, Dr. Mustapha, for this amazing and informative presentation. Like I always said, when you're conducting a research, I post some steps that will guide you. And at the end, if you're not too sure, ask someone who you know is an expert in the field. Then we have a PSI discussion community. If you are having some issues with your research, the design, the board statistical questions or anything, please, we have shared the link in the chat box. Please, when you join, if you have any issue regarding your research or any questions, please post it on the WhatsApp chat. And I assure you, we have so many experts that are happy to give you an answer and guidance. In the absence of any other questions or observation, I will call on Dr. Basira Kankia to give the closing remarks and present the certificate to our guest speaker.
Oh, thank you very much, Kai. All I have to say is wow, wow. This has been very enriching. Thank you very much, Dr. Mustapha. So this has been really an insightful presentation, and it's been a wonderful 2 hours where complex things, I believe, for me, I always look at statistics as something complex. You've been able to make it very simple and straightforward, and we really appreciate. And it's important, as Dr. Jatau mentioned, let's keep the conversation going. We have the PSI community discussion group, so that we can all support each other through our research journeys and to apply what we've learned to make meaningful contributions to the field of health sciences.
Okay.
Dr. Jatau, please, can you share
Yes, Dr. Kakia, sorry, with your permission, I've seen Dr. Isa Mohammed Sabo, who is a consultant at Aminu Kano Teaching Hospital, and I think a senior lecturer at Bayero University, Kano. Dr. Isa Mohammed Deneja, are you around?
Hello, Professor Ibrahim Jatau.
Yeah, there, please. Can you present the certificate?
Thank you very much. Professor Ibrahim Jatau has been a colleague right from secondary school. Please, I'm very sorry you can see the audio I have. My daughter is kept on disturbing me. Please, sorry.
Oh, okay, that's fine. I wanted you to present the certificate, but that's fine.
Thank you very much. Sorry, please.
Okay, that's fine. Okay, Dr. Kankia, go ahead.
Okay, so on behalf of all our senior colleagues, our professors here present, we really appreciate you, Dr. Mustapha Mohammed, and we'd like to present this certificate for being our guest speaker today. Thank you very much.
Thank you so much, Dr. Basira Kankia. I really appreciate you presenting this certificate to me. And I would like to also thank PSI for organizing this educative and interactive fora. So I believe this is an opportunity for us to look forward and see more and more of these activities from PSI. Mr. President, you have been doing very wonderful. So we believe that may Allah continue to strengthen you, to continue to bring us together and benefit each other in science and otherwise. So thank you very much.
All right. All right. Thank you so much, everyone, for finding time to attend this webinar. At least we kept you guys for constructive 2.5 hours of constructive information flowing. Thank you so much to our guest speaker for finding time to share his knowledge and expertise to us, and all other members who attend this